Hello, this is my Lab 2 presentation on motion of a falling object by Math Madness. This lab explores falling motion experienced by an object, meaning that the object is accelerating towards the ground. This includes a real-world demonstration of Newton's second law of motion, as the net force equals the sum of the forces of drag and gravity. The law is also known as the momentum principle, and it is applied multiple times in this lab, including to update the position and velocity of our objects. This lab helps present the forces of gravity on an object and how the drag force affects the motion when passing through a medium, in this case air. To demonstrate this phenomenon of falling motion, I recorded the movement of a physical object when released in midair and then coded a simulation that would model the same motion digitally. After executing the experiment, I found that the computer model was able to, when considering drag forces, was able to closely predict the position at any given time. However, if drag force is ignored, there's a significant deviation in the results. The data collection for this lab began by recording the falling motion of an object, in this case a gift card. Afterwards, I uploaded the video in a tracker, set the coordinate scale, and placed center mass points, and then took this data, graphed it, and extracted the necessary data to complete the coding, which I will explain more in the following slides. With the plotted data from both the physical object and simulations, I was able to make some observations. I saw that the physical object's acceleration reduced over time, which is likely the result of the drag forces that were only considered in certain models. The physical object followed the predicted motion with the drag quite nicely. When drag is not considered, the object travels significantly further in the same time interval. Seen here is my glow script code in VPython. I first input the initial position above the ground and then set the total time to match the observation. I also implemented the momentum principle to update the position and time based upon the forces on an object at any given time. I also used the turbulent drag formula to solve for the drag force and simplified gravitational formula to solve for the force of gravity. As part of the drag force, I defined a b variable. I set this to equal 0.025, which results very closely observed motion, and was solved for by trial and error. I also changed the delta t value, which made the code output the same number of data points as in tracker, which helped when combining data sets into a single graph. On screen now is a screenshot of the two completed simulations. On the left is my model with drag, on the right is my model without drag. You can see the arrows show the direction of forces being applied on each object. The output force can be found on the previous observation slide. When the simulation can be found in the link on screen or in the submission page. Improvements. When considering drag, the observed and simulated motions did not perfectly match up, even when considering drag. This discrepancy could be reduced a few of the following ways. Firstly, we could solve the drag force using a different, more complicated formula, as seen to the left with d equals the following formula. This formula has more variables than the one used in my model, and thus could have a more accurate result. Additionally, a high-speed camera could be used to provide high-detail footage, even at high FPS, which would reduce the number of visual artifacts in recording, which impacted data collection. One additional means of improvement is to retest using a non-rotating object as my physical object. A gift card rotated slightly when it fell, which means that different amounts of drag were experienced than the model predicted. This is likely the most valuable improvement. Further thoughts. As seen to the far left, the model with drag and the observed motion shows an initially steep change in velocity, which trends towards a delta v of 0, meaning that the force also approaches 0. The model without drag, seen on the right, also has a consistently increasing velocity. Drag must be considered to predict terminal velocity, as drag is necessary to cancel out the forces of the downward gravitational force. As the velocity versus time graphs show, regardless of the initial velocity conditions, the forces eventually release equilibrium, resulting in a terminal velocity, which is always the same regardless of initial velocity conditions. This is because the terminal velocity is a result of the balancing of gravitational and drag forces. Thank you.